Okay, so today in workshop we didn't get a chance to properly go over this worksheet, and due to the pace of the course on next Tuesday when we meet, we have to move on to kinetics. So I figured rather than writing out a key and posting it onto Blackboard, doing a video of me talking through me working out the worksheet would be more beneficial for y'all to do. I'll have timestamps in the description for at the times when I start each problem. So it'll say problem 2 starts at 4 minutes, whatever. So you can skip around. Make that easy for y'all. Now I'm fortunate enough to have access to software that records my screen, to have a microphone, and to have a pen tablet here that I can write stuff with. But I'm not fortunate enough to have the time to go back and edit. So I'm going to do this in one take. It's probably going to have a bit of a pauses, or I'm going to trip over my words and, double back and say it again. But if we meet in person, it's not like I can have second takes or whatnot, right? So nonetheless, we're just going to go through this. And if you have any questions, post them in the comments. Leave a timestamp where your question popped up and do an explanation, and I will reply to you on the video, right? Okay, so let's get through number 1. I'm going to get out my fancy dancy highlighter. So it says a solution is prepared by dissolving 27.0 grams of urea. Cool. And 150 grams of water. Awesome. Highlighting things is great. It says calculate the... I'm going to change colors because this is what the question is asking me. Right? It says calculate the boiling point of the solution. Right? Cool. So that is what the question is asking me for. It goes on to give me some constants. Right? The boiling point constant of water, Kb, and the boiling point or freezing point constant for water, Kf, right? The colligative properties. Take special note of the units, and we can carry on, right? So for colligative properties like boiling point, raising or freezing point, depression, we're going to be using a linear approximation to these, right? So of the form y equals mx plus b. So to do this, we need the new y is going to be our new boiling point, right? So the boiling temperature is equal to our m is going to be some constant, right? For a line mx plus b, m represents your slope, and the slope of this line that we're going to be using is kb, right? Which is the same thing as this kb here. Our independent variable is going to be the molality of the solution. Actually, that's represented by an m, not an x. Right, so the molality, in this case, it's of the urea, right? Of urea, and then plus the B would be the normal boiling point of our thing, right? So I'm going to say some temperature T naught, or the boiling point initial, right? So it's important to note that the initial boiling point is equal to TB when there's no urea, right? All right, so I'm going to note that as evaluated when M urea is equal to 0. In other words, that is pure water, right? When our water is pure, 100 degrees Celsius. So the form of this equation you'll see in your book, what they do is they subtract the TB naught. So this implies that TB minus TB naught is equal to Km, or Kb times m of urea. And then they say the boiling point minus your initial boiling point is your change in boiling point, right? So this is the equation that y'all are familiar with. However, the question asks us calculate the actual boiling point, not the change in boiling point. So it's useful to think about expanding that delta T. Okay, so let's think about what we know, what we don't know. We know the initial boiling point, or boiling point of pure substance, right? 100 degrees Celsius. We know, well, this is, we know Kb, right? We're looking for this. We're looking for our boiling point. And so we have to find the molality of urea. Okay. So let's find that, right? So the molality of urea would be the moles of urea over however many kilograms of water you have, right? Okay, so it says here you have 27.0 grams of urea. We can quickly calculate the molar mass and convert this grams to moles. Right, so if we do that really quick with air quotes, you can't see the air quotes, we have 2 nitrogen, so that's 2 times 14, and I'm going to use rough approximations for these. It's not terribly important to have super accurate values. What's important is that you know what to do with those values, right? So I have 2 nitrogens. I'm going to add that to the 4 hydrogens that we have, and hydrogen has a molar mass of 1. I'm going to add that to the 1 carbon that we have, right? Molar mass of carbon is 12. I'm going to add that to the molar mass of however many oxygens we have, which is 1 as well. Molar mass of oxygen is 16. Right, so if I get out my calculator, and by my calculator, I mean my computer's calculator, right? So we have 28 plus 4 plus 12 plus 16. 60. Awesome. And it might be like 60.01, but that's okay, right? And very important, write down the units next to that number. Right, so 60 grams per mole. So what we can do is we can start with 27.0 grams of urea. Multiply that by 60 grams of urea for every 1 mole of urea. There we go. So now we have the top bit, moles of urea. So now we have to do is divide that by however many kilograms of water that we have, right? If we have 150 grams of water, we have 0.15 kilograms of H2O. So that turns out to be, oh, let me get out my calculator again. Right, so we have 27 divided by 60 divided by 0.15, which is 3. Yay! Awesome. So now to finish this problem off, we have no more room. So I'm gonna erase. No, I'm going to use the magic of computers to simply just move this out of the way. Man, I wish I can do that in real life on a sheet of paper. Very useful. I'll be a bit slow on my laptop, but that's okay, because it still gets done. Could also be using multiple colors. I'll probably do that for the next problem, right? Okay, so then, if I'll do it right now, why not? Right, so your boiling point is equal to, Kb is 0.51, and this is degrees Celsius, kilograms per mole. We're going to multiply that by the molality, which is 3, and that's in moles per kilogram. And then So here it's important to see that your units properly cancel out. So the units on the left-hand side is degrees Celsius. And here we have moles cancels out with moles, kilograms cancels out with kilograms. So we're left with degrees Celsius here, right? So the units have to match. That's perfectly fine. Right. And the last thing is we have to add, let me change back to my color. We have to add our 100 degrees C. And we will find that the new boiling point is 101.53 degrees Celsius. That is our answer. It's not very much room to write your work, I realize. But to be fair, we could just get out a separate sheet of paper. Right? Nothing keeping us from doing that. Okay, so let's move on to the second question. Make our pen be a reasonable color. Let's choose blue. Why not? Why not blue? Okay, so it says calculate the freezing point and boiling point for each of the solutions below. You can assume complete dissociation. So we have thingies. Now, another important note that I forgot to mention in the first one is this over here is not 100% complete. It is correct, but it's not complete. I am missing my Van Hoff factor I. Now, in this particular problem, the Van Hoff factor was 1, right? And I know it was 1 because urea, our compound here, is a covalent compound, right? N, H, C, and O are all nonmetals, so this is bonded covalently. Therefore, it does not dissociate in water, right? So our Van Hoff factor was 1, so then 1 times Kb m urea is the same thing as just Kb m urea, right? So that was perfectly fine. But for these problems over here, for number 2, NaCl is no longer a covalently bound compound, right? So if we're using let's calculate the boiling points first, right? And again, we're using water, so the boiling point of water, pure water, is 100 degrees Celsius. And the freezing point of pure water is 0 degrees Celsius, right? Just for reference. Okay, so or I should say TB naught, TF naught, right? It's just that is our initial boiling and freezing point, right? So for our boiling point for the first one, TB is equal to I Kb m NaCl plus TB naught, right? Their Van Hoff factor for sodium chloride is 2 because sodium chloride dissolves into 2 separate ions, right? One thing becomes 2 things. So to give this numbers, and the Kb, we can use the Kb from the previous problem. It's the same thing. Yes. So let's go ahead and do that. So TB is equal to 2 times 0.51 times, I forgot the molality of HCl. Right, I need my MNaCl. So let's move this down a little bit and calculate the molalities for each A and B. Let's do that in orange, right? So MNaCl is equal to, we're going to do the same exact dimensional analysis that we did for the previous problem. So we have 5 grams NaCl, right, just like we did over here, times 1 mole NaCl over, we'll have to figure out the molar mass of NaCl. I believe it's 54.44. I should probably check that. I'm pretty sure. Okay. And we multiply that by 1 over however many grams of water or kilograms of water we have, right? So that's 0.025 kilograms H2O. And then we can compute that. Right, handy to get a calculator again. So, that's a scientific calculator for whatever reason. That's cool. Right, so 5 divided by 54.44 equals that, divided by 0.025 equals that. Right, so our molality is 3.67 moles per kilogram. Right, moles NaCl per kilogram H2O. Okay. Wow, I don't have enough room for this. Let's move this up again. It just disappeared. Okay, I'm going to squish this. Oh my gosh. Can I? There we go. Awesome. And can I squish this one? And then can I squish this one? And then can I... No. Squish that one. There we go. Now we're cooking with petrol. Go all the way around. And then move this over here. It didn't quite work. Now it works. Yay! Okay. Let's go ahead and do the molality for part B as well, right? Because that's not going to change. AlNO3, and again, very similar dimensional analysis. And I am going to have to look up a periodic table to get this molar mass. I don't remember the molar mass of aluminum off the top of my head. Right, aluminum compound. That's the only aluminum compound we have, so I could put dots there. It's fine. Okay, and to get the molar mass, I am gonna use Google. Right, so molar mass of AlNO3. Go! Yay! Let's see, I want to make sure that this is not the hydrated version of that, right? Because I know that it forms hydrate. Right there, hydrate. Right? I do want the anhydrous version of this. Okay. Does it give me the number? Okay, there we go. I'm going to round it off to 213. Right, so 213 grams of aluminum nitrate. That's nitrate, right? Yeah. Okay, and then this solution is in 0.015 kilograms of water. Okay, and then calculator. Can I change this to normal calculator? It's too big. Awesome. Oh. There we go. Much better. I'm just going to use my number pad, right? So 15 divided by 213 equals. And then that divided by 0.015. Oh, my enter key does not work. Great. 4.69. And this is moles AlNO3 per kilogram H2O. Awesome. So let's switch back to blue, and then we can finish this problem. First off, I'm going to move this because I know I'm going to run out of space. Of course, it didn't actually go. Okay, cool. So here we're going to use this is for sodium chloride for part A. So we're going to use 3.67 and then plus 100 degrees Celsius because this is my boiling point. And that equals some number. Let's run through that calculation really quick. So that's 2 times 0.51 times 3.67 equals, and then plus 100. Alrighty, so that's 103. Oh, I missed the oh gosh, so many calculators. Oh, that's not the one I want. That's not the one I want. Have I been opening up a new calculator every single time? Oh gosh. 7.4. Now, admittedly, I am ignoring sig figs completely. Yeah, I'm ignoring sig figs. Okay, let's do the freezing point. Right, so I is going to be the same. Actually, this is going to be the same. Now, it's important to note for the freezing point, this string of thingies right here is actually negative, right? Because your freezing point, the thingy is called freezing point depression, right? So if you add salt to water, you lower the freezing point. So it should be your initial freezing point minus IKF. That's supposed to be an M. MnACl. Right? So this is 0 degrees Celsius minus 2 times Kf from the previous problem is 1.86. And our molality is the same, 3.67. Right? And if we run that, let's not open up a new calculator. Oh, I forgot how to clear it. There we go. It's super wide again. Right, so 2 times, I know I've ignored the negative, but I will tack that on at the end. Right, so 0 minus 13.65 is negative 13.65 degrees C. Yes. Okay, I will do the other two in a different color. Green. I haven't used green. That's a very light green. I'll do dark green. Okay, so for the aluminum, right? So the boiling point for the aluminum is IKB molality of AlNO3, which we have, and then plus the boiling point of water, right? So your Van Hoff factor for ammonium nitrate, notice ammonium nitrate has 4 ions, 3 plus 3 NO3s, 1 minuses, right? So this implies that I is equal to 4, your Van Hoff factor. So we're going to have 4, Kb is still 0.51, and your molality we calculated over here to be 4.69 at the normal boiling point, and we can do that, right? So we have 4 times 0.51 times 4.69, add 100, and we get 109.6. Right, likewise, our freezing point is the original freezing point minus our freezing point depression. Right, so that's equal to 0 degrees Celsius minus 4 times Kf is still the same, and our molality is still the same, right? 4.69. So let's do that. 4 times 1.86 times 4.69 is equal to 34.89. It's pretty big. Makes sense. We have 4, which is 16, and then times a quantity that's mostly 2, right? So we should expect it to be around 32. Right, so 34 or negative 34.9 degrees Celsius. Right, so just for reference, these two are for part A, right, boiling point, freezing point, and these two are for part B. All right, this is turning out to be a very colorful key, which is pretty cool. Okay, let's keep moving on. Right, so it says use the following data for 3 aqueous solutions of calcium chloride. Right, so it's important to note we have aqueous solutions of calcium chloride. And let's change my color. Blue, I like blue. Calculate the apparent average value of the Van Hoff factor. Okay, so going back to before, we know that delta T is equal to I, and we're dealing with freezing point here, so KF, and then times our molality. Right, this is molality of calcium chloride. Okay, so like I said before, right, these equations are a line, and your slope here is IKB, right? Your slope, right? If delta T is a function of the molality, then your slope for this function is equal to IKF, right? And another important note is that since we're dealing with an aqueous solution, our solvent is still water, right? So we can still use the KF is equal to 1.68 or 1.86. I just totally reversed those numbers. And then I wrote over the numbers as if that was going to make it better. Right, 1.86. Right, so here it gives us a table, and these are our x values and y values respectively. So we're going to calculate the slope. Right, so slope, remember, is y2 minus y1 over x2 minus x1, right? So we need 2 points. This is a point, and this is a point, right? We take those 2 points, and we perform this operation, right? So this is y2, y1, x2, x1. Okay, so 0.440 minus 0.110 over 0.0910 minus 0.0225, right? And this is going to be some number. Now, and this is going to be some I times KF. However, this is gathered data. There's experimental error. So we're going to have to use as much data as we have, right? So it's not sufficient enough just to do this between 2 points. We're going to use all pairs of points, or all consecutive pairs of points, to eliminate error. Calculate IKF for each consecutive pairs of points, and then average those values together to get an averaged IKF value, right? So we're also going to not just perform this on these 2 points, but we're also going to do that on these 2 points as well, right? Because those are consecutive points, right? So this is also equal to, or for our second data point, so to speak, 1.330 minus 0.440 over 0.278 minus 0.091. All right, let's plug those into a calculator. Handy dandy calculator. I forget if I can do brackets on these. Yes. Awesome. Right, so 0.440 minus 0.110. My calculator probably hates me for typing in a 0 there. Right, divided by parentheses 0.091 minus 0.0225. And let's make sure that put it in that parentheses correctly. Yes, it did, right? So 0.0685. 0.0685. And it's also important to note I should be approximately an integer, right? Can't have half of an ion floating around. Wait, let's do that for the second one. It should be close, but probably not equal to. Oop, I forgot my parentheses. 1.33 minus 0.44 divided by 0.278 minus 0.091. Okay, nowhere close, right? Cool. Let's roll with it. So we have 0.187. Off by a factor of 3. Interesting. Wait, did I type in this right? Yes. Checking. Yes, it is. Okay, so that's our value. We're going to average those two together. Right, so this plus 0.0685 is equal to that. Divide that by 2. So equal to 4 point something. Hold on. 0.0685 plus 0.187 is equal to, there we go, divided by 2. Right, so 0.128. Round it off to that. Right, so that's equal to IKF. IKF, we said was 1.86. Right, so then our Van Hoff factor is equal to 0.128 divided by 1.86, which is not an integer. Clear. 0.128 divided by 1.86. Nope, that's not what I meant to do. I'm going to try the reciprocal of this and see what happens. 1.86 divided by 0.128. 14. Okay, maybe that's completely wrong. Okay, hold on. Maybe I have calculated one of these incorrectly. So what I'm going to do is I'm going to, instead of punching everything into the calculator at once, can you please select that? Is I'm going to take it a little bit slower. I'm going to keep my values that I have just for reference. But really, when I got values that were really different like that, I should have been suspicious that I punched in something wrong. And usually that's what happens. We just punch in the wrong things. Right, so in the numerator, that's 0.33. In our denominator, bring out my calculator, 0.091 minus 0.0225. equals 0.0685. See, this number was this number, so that definitely was not correct, right? So there is our error, possibly, unless I made another one, right? 0.33 divided by 0.0685 is 4.82. Cool. Yeah. So let's erase this. Right, 4.82. Awesome. Now, it's also important to note, calcium chloride, we know what the Van Hoff factor for that is. It's going to be approximately 3. Right. Okay, so let's redo this then. 1.33 minus 0.44 is 0.89. 0.278 minus 0.091 is equal to, oh, I didn't even check if that was like correctly inputted. 278 minus 0.091. Okay, cool. 0.187. Right, so 0.89 divided by 0.187. Cool. 4.75. There we go. Those are much closer together. 4.75. Erase, erase. Cool, so let's erase this and erase that. Right, our KF value is still the same, so that's fine over there. So we have to average 4.82 and 4.75, so add them together and divide by the number of things we just added, so 2. Right, so 4.785. And then divide that by 1.86. A little less than 3. Now, it's important to ask yourself, does this make sense? 2.57. Thing out of the way. I don't know how to move that. There we go. Does this make sense, right? So intuitively, we should have known that this is about 3. 2.57 is less than 3, which is okay. And this is real experimental data, right? So beforehand in the previous problem, it very appropriately said that you can assume complete dissociation, right? So all of the sodium chloride ion pairs, I was going to say molecules, but they're not molecules, right? All of the sodium chloride ion pairs split up, every single one of them, right? Van Hoff factor was 2. But here, this is real data, right? So we could argue that, well, maybe not all of the calcium chloride dissociated, in which case the Van Hoff factor is at a maximum 3, right? Because it definitely can't split up into more than 3 ions, right? A lot of it split apart and became 3 ions, but maybe much of it stayed together. Or maybe calcium chlorine, right? Calcium and a chlorine stayed together, and then just one Cl minus came off, right? All of that is possible. That's the problem with dealing with real data, right? So we have a Van Hoff factor of 2.57 for this experimental data, right? An important thing to note, if they were to give you more data points, sometimes get the question, do I have to use all of them? Yes, you have to use every single one of them, right? Think about, out in the workplace or whatever, somebody went through and gathered all that data, their company or whoever you work for spent money on the person who gathered that data, and then for you to not use that data, that's a misuse of resources, right? You're going to get fired. You're not going to be very well appreciated by the technician who gathered that for you. Whoops, I didn't want to go that far. There we go. Anyways, moving on. So number 4, a 0.15 gram sample of protein, some mysterious protein, is dissolved in water. The solution has a volume of 2 milliliters. The osmotic pressure is that many torr and that Kelvin. It is at that Kelvin. Calculate the protein's molar mass. Right, so we're going to use our osmotic pressure. Let's see if I can remember it. Right, MTV? No. There's definitely a T in there. R. There we go. MTR. And actually, I just realized this has the form of the ideal gas law, right? Osmotic pressure is a pressure. The molality is some moles over some volume times the temperature times R, right? So if we multiply by our volume, we have PV is equal to the number of moles. We'll put it in a form that's more familiar, RT. Right, so there is a connection. This isn't just some random equation. It is connected to the ideal gas law in form, at least. Right. Again, I don't know why they use a capital pi. Probably because pressure starts with a P and pi represents P in Greek. So, yeah, ways to remember. Right. So, anyways. So let's plug in what we know. 18.6 torr. Now I know the value for R in liter atmospheres per mole Kelvin. So R is equal to 0.082 liters atmospheres per mole Kelvin. If you know it in other units, you can definitely use that. And I think you will be given this constant. However, it makes your work a lot quicker if you just know it off the top of your head, right? The important thing I get out of this is that this unit of pressure is atmospheres, and this unit of pressure is torr. So I need to rectify one or the other. I'm going to convert the torr to atmospheres to make my life easier, right? So 18.6 torr times 760 torr per 1 atmosphere, right? So that's my osmotic pressure is equal to the molarity of the protein, right, times the temperature. I know the temperature. And also in our gas constant, the temperature is in Kelvin. So this temperature right here has to be in Kelvin as well, right? Celsius and Kelvin, when they're multiplied, do not cancel out. Let me go ahead and write my units there. Right. Also, it's just Kelvin. It's not degrees Kelvin. Right. And then 0.082 liter atmosphere per mole Kelvin. Okay. So you might ask yourself, this is asking for molar mass, but I don't have molar mass in this equation. And also I have like volume here and grams here, but that doesn't show up anywhere in here. Well, we have this M term, and we can expand that out, right? So 18.6 over 760. This is in atmospheres now, right? That's some number. We know what number that is. So molarity is going to be moles of protein. I'm going to call it protein P. Over liters of solution. And 298 times 0.082. And both of those numbers multiplied together have units of liter atmospheres per mole. It's not necessary to have your units while you're doing these calculations, but it helps. Right? It helps. And also notice liters of solution cancels out with liters, moles cancels out with moles, you're left with atmospheres. Let's run these through a couple of calculators. Run them through a couple of calculators. Yeah, that makes sense, right? Let's clean up some of these numbers, right? 18.6 divided by 760. And I'm going to move this to up here. All right, so that's 2.38. Moles of P. I still don't have moles, but I do have liters of solution, right? So I'm going to split up my liters. Just put a 1 up there so I can put the liters on the bottom. I have 2 milliliters, so that's 0.002 liters. Now I have to get my moles in here. I have grams, and I want to calculate molar mass. Right, so molar mass is grams per mole. I need moles up here. So this implies that moles is equal to your grams divided by your molar mass. Right? Cool. So if we take our grams of protein, so 0.15, and then this is going to be my molar mass on the bottom, and then multiply that by the other numbers. Equals 24.44. Erase this. Oh, I probably should have kept that actually. That's okay. It doesn't matter. Okay, so at this point we can do the bit of algebra to solve for molar mass. Right, so molar mass would be equal to 2.38 times, put these in parentheses so it's easier to read, 0.002 divided by 0.15 divided by 24.44. Whoop, didn't want to do that. There we go. Okay, let's do this carefully, right? 2.38 times 0.002 equals, and then divided by 0.15 equals, cool, divided by 24.44 equals. Yes. Okay, so 0.0. This seems wrong. I expected this to be very large because it's a protein. Molarity is moles of protein per liter. Moles is grams divided by molar mass. Yes. Grams by molar mass, that's our volume in liters. And then 298 Kelvin and 8.082. Okay. Trust in the numbers. Right? So 0.0013 grams per mole. There we go. This thing I don't know what it does. There we go. So this bothers me because a protein usually consists of many, many carbon atoms, right, and other atoms as well. But according to the calculations we've done, this protein is, well, just to put this in perspective, one carbon atom weighs 12 grams per mole. I think our answer is wrong, but can we find out where it's wrong? Possibly. Let's figure it out. Okay. So 18.6 torr, 760 torr per atmosphere. Let's validate that. This is going to be a long video. Okay, so torr in atmosphere. 760. Right, so 760 torr per 1 atmosphere. Okay, so that's not incorrect. Let's look at the value of R. Whoop, that's my calculator. Right, so ideal gas constant. 0.082 liter atmospheres per mole Kelvin. So that's not incorrect. Okay. So this is correct over here, and Kelvin is correct. So then where could I have gone wrong? I have an idea. Let's erase this stuff over here. Right, and then what we're gonna do instead, in fact, let's erase this and all of that. Cool. Right, so instead of doing this, let's just solve for, actually, let's erase this one too. Let's do this with variables. Oh, come on. No, you want to circle it. And delete. Let's do this with variables before we start plugging in numbers, because stuff gets messy. Right, so our osmotic pressure is equal to molarity TR. Maybe that's wrong. Let me go validate that really quick, because that could very well be wrong. And yes, I'm Googling it rather than looking at the textbook. Yeah. Right. Van Hoff factor. We're going to assume that doesn't associate, right? So pi is equal to m sol u r t. Good. That is correct. Awesome. Is there any special thing with the pressure? Like maybe it's like whatever. It's a colligative property. Yeah, that's cool. Like is it like gauge pressure? I do not think so. No. Okay. So this is correct. Let's solve for m here. Right? So osmotic pressure divided by TR is equal to m, which is equal to mole of protein over liters H2O. All right, liter solution, right? Right, so we know liters of solution. I'm going to move that to the side. So moles of protein is equal to volume times our osmotic pressure divided by the temperature times R. Right, so moles, that's our mass divided by our molecular weight. Okay. Whoop. Wait. It's equal to V osmotic pressure TR. So now let's solve for molecular weight. Going to divide by mass, right? So 1 over mW is equal to V pi TR mass, right? So then our molecular weight is equal to our temperature times ideal gas constant times the mass of our stuff divided by a volume in liters times our osmotic pressure in atmospheres. Now let's plug this in. Okay, so that would be 298 times 0.082 times 0.15 divided by 0.002, right? 1, 2, 3. 1, 2, 3. Gotcha. And then our osmotic pressure, again, converting this to... Oh, it's times. That's where we went wrong, right? 1 torr... No, that's not where we went wrong. Hold on. Okay, so 760 torr is equal to 1 atmosphere. So then 18.6 torr is equal to 18.6 over 760 atmospheres. So 18.6 divided by 760. Okay. And cool. So let's plug all this in and then hope that we don't get a molar mass that's smaller than a proton. Right? Because something's probably wrong with that. I'm going to do the inner parentheses first. Divided by 760. Right, so... This gives me hope because this right here, this 0.002 is on the denominator, and that's going to make our fraction quite large. And also we have a 0.024 in our denominator as well. Right, so that's going to make our fraction quite large. I'm not sure where we went wrong before, but at least we've worked it out, right? That's the important bit. The fact that we've worked it out, and 3.665, and that we have a solution. Right, so 3.665 divided by 0.0002. Oh, there we go. Almost added an extra 0. And then divide that by 0.024. There we go. So now we have a ridiculously large number, but that's perfectly fine. Again, these are proteins, so they're possibly hundreds of carbons long, right? And oxygens and whatnot, right? So they're expected to be very, very large. So 76,400, we'll round that off to that, right? 400 grams per mole, and I'm very confident about that, right? Okay, so let's go over what happened there. So we started off with this correct equation, and I made the mistake of plugging in numbers first and then manipulating stuff with the numbers there. That just crowds up what I'm looking at, and that leads to mistakes. Can lead to more mistakes. So do the algebra without numbers before you plug in, and plug in last, right? Keeps everything clean. And we got a reasonable number, a number that's not smaller than a proton. Cool. Alrighty. So let's keep on scrolling down. Okay, so it says what mass of glycerin, give us the molecular formula, it's good, probably unimolar mass, must be dissolved in 300 grams of water to result in a solution with a freezing point of 2.0 degrees Celsius, right? How much is needed to raise the boiling point to 3 degrees Celsius? Oh, to raise it by, that's a typo. How much is needed to raise it by 3 degrees Celsius? Glycerin is a non-electrolyte, meaning it doesn't dissociate, aka our Van Hoff factor is 1. In fact, I should write that. Non-electrolyte, I equals 1. And it gives me the Kb and Kf for water again, right? Because water is our solvent. Cool. Okay, let's very quickly solve for the molar mass of glycerin. So we have the molecular weight is equal to 3 times the molar mass of carbon, because we have 3 carbons. So it's 12 plus 8 times the molar mass of hydrogen. It's 1 plus 16 times the molar mass of oxygen. I said that backwards. This is 16 and I have 3 of them. There we go. Right, so that is equal to, clear? It would be 8 plus 36 plus, what is 16 times 3? 24, 54. 98. 16, just to verify, 16 times 3 is indeed 54, right? Oh, it's 48. Really? Oh, shit. Okay, so 48 plus 8 plus 36. Man, I wish I had some editing software. Okay, 92. Or some editing software that didn't take an age to learn how to use. There we go. Cool. So we have a solution with a freezing point of -2. That is identical to a freezing point depression of -2, because the freezing point of water is 0 degrees Celsius, right? But we'll go through the thing, right? TF is equal to IKF. Oh, no, hold on. TF naught, right, our normal freezing point, minus IKF times our molality. I'm going to call it molality of glycerin with a G, right? Our freezing point of water is 0, so, and we know the TF, right? So that's -2 is equal to 0 minus 1 times 1.86. And we need to get our molality of glycerin. I'm going to do that in a different color. Let's see which one. Orange. I like orange. Okay, so molality of their glycerin is equal to the moles of glycerin. So let's start out with, it asks us for the mass. Oh, cool. Okay, so let's leave that. Let's leave that as a variable. We'll call that x. So let x be the mass of glycerin. Right, so this is x grams of glycerin. Right, I'm going to leave that there just because. Right, so times, we need this to be moles, right, because we're doing moles of glycerin per kilogram of water. So times 92 grams of glycerin per 1 mole glycerin. And then multiply that by 1 over 0.3 kilograms of H2O, right? So our mg, and it's going to be in terms of x, which is perfectly fine because we want to solve for x. Is going to be x divided by, I'm just going to do this multiplication really quick, 27.6. It's going to be x divided by 27.6, right? Multiply the top, we have x times 1 times 1, and then divide by the product of the bottom, 92 times 0.3, we get that. All right, so let's plug that in for this. And blue, add a blue. Right, so x, erase. Oh, select the pen, there we go. X divided by 27.6. And that is that, right? So we have an equation with one variable, x, and we can solve it. Right, so we get minus 2 is equal to minus, let's go ahead and I'm making the mistake again of doing this with numbers right off the bat rather than working with just the variables to begin with. I have not learned from my own mistakes. But that's okay. Right, so 0.067. Let me just double check that because my brain. There we go. And then, so I divided 1.86 by 27.6, so I should have an x left over. So this implies that x is equal to, negatives cancel out, right? So we just divide 2 by 0.067. Right, so close to 30 grams, right? It's 29.9. Right, so this is to lower the freezing point. Now for the boiling point, which is hot, so I'm going to use red. So it's kind of cool, right? This is going to be a separate calculation in total, right? So TB is equal to IKBmg plus TB naught, right? So we know the initial boiling point of water, and we know TB, right? We want it to, actually we just need it to be raised by 3. So we don't even need TB naught, but we just need to do the delta T. So in other words, TB minus TB naught, right? Just your delta, here's your change in temperature. Okay, so here we have, so this implies that 3, right, 'cause that's our change in temperature, is equal to, I is 1, KB is given, 0.51, mg, our molality of glycerin, is x divided by 27.6, where x is the mass of glycerin. So we can solve for x. So that's 3 times 27.6 divided by 0.51. And we can run that calculation real quick, can't we? So clear that. 3 times 27.6 equals 2 divided by 0.51, which is approximately multiplied by 2. So 162. We'll leave it as that. Right, 162 grams. Right, okay, so this is for boiling point, and the other one, the one in blue is for, not purple, blue. This is for that was challenging to write like that. That was for freezing point. Okay. I'm going to take a drink. I've been talking a lot. How long is this recording so far? About an hour. Wonderful. All right, we're almost done. Oh gosh, we have 3 more. Woo! Okay, cool. So it says sodium chloride is going to be added to a electric kettle, half filled with water. Kettle has a maximum volume of that. Kettle can only raise temperature to this. 200 grams of sodium chloride is added. Can we boil the water? Well, let's figure that out. Right. So our volume of water is equal to, well, it says the kettle can hold 1.5 liters and it's half filled. So we have 3/4, 0.75 liters of water. And water has a density of 1 kilogram per liter. So this implies 0.75 kilograms of water. Right, numerically they're the same. For pure water, they're the same. Oh, it already says that, right? Kilograms per liter. By the way, kilograms per liter is numerically identical to grams per milliliter, right? Multiply and divide by 1,000. Okay, so we have 200 grams of sodium chloride. So let's convert that to moles, right? 200 grams NaCl times 54.44 grams NaCl per 1 mole NaCl. And let's go ahead and calculate the molality. Kilograms H2O is equal to, right? So this is M. And let's do that real quick. 200 divided by 54.44 is equal to. Divide that again by 0.75 equal to. Right, so our molality is 4.9 or 4.9. And this is moles per kilogram. So now we just need to calculate the new boiling point of the water. Right, so TB is equal to, sodium chloride is an electrolyte, splits into 2 things, so 2 times KB times M plus 100 degrees Celsius, our normal boiling point of water. KB is the same KB that we've been using for water, right? So that's 2 times 0.51. Molality we just calculated, so 4.9 plus 100, right, which is 2 times 0.51 times 4.9 plus 100. Whew. That is really close, right? So our new boiling point is 104.998. So I think for this, we're going to have to look at how many sig figs we need to give an answer to this. Okay, so for our molality, we have 200 grams of sodium chloride. That has 1 sig fig, right? So then this number should have 1 sig fig, which means this number should have 1 sig fig, which means, oh, let's move this down. Which means that this whole section right here, because we're multiplying, should all have 1 sig fig, right? So that should be 5 plus 100. Now, addition rules are that we keep the lowest digit, right? This has less digits. Hold on. This has less digits. There we go. The other one does. So we keep that one. So essentially we just ignore the 5. Well, either way, it's about 105-ish. And it's pretty close. Now, it is boiling at 105. As far as sig figs go, I think we can only report... No. 100 degrees Celsius is defined to be the boiling point of water, right? That's not experimental. The Celsius scale is defined as 0 is the freezing point of pure water, and 100 is the boiling point of pure water. That's how that scale was defined. So 100 is an exact value. 105 is our number with the appropriate number of sig figs. And this water would boil at 105 degrees, right? So yes, it can boil. It can boil, but barely. Barely boil. Okay, next one. It says the vapor pressure of pure benzene is that many atmospheres. 10 grams of non-dissociating, non-volatile solute is added to that much benzene, which is at the same temperature. The vapor pressure is now that. Determine the molar mass of the solute, right? So we're doing with vapor pressure and impurities that cause the vapor pressure to change. We're going to be using Raoult's law, right? So the new vapor pressure is equal to the mole fraction. So the vapor pressure of benzene is equal to the mole fraction of benzene times the pure component partial pressure of benzene, right? So this P star, you'll see it notated a couple of ways, right? So P star benzene is equivalent to the saturation pressure of benzene, which is also the vapor pressure of pure benzene, right, at equilibrium or whatever. It's a different notation. They mean the same thing. I like to use P star because that's the way I've been taught. Okay, so question is, so we have the new vapor pressure, right? This is the new vapor pressure after the stuff has been added. Actually, I'm going to keep this as variables because I'm smart, right? We have this. We don't know what that is, but we can expand it. We want to determine the molar mass, and we have a bunch of gram stuff. So let's divide by the pure component vapor pressure, right? PB over PB star. Right, and let's expand our mole fraction, right? So this is moles of benzene over moles of benzene plus moles of stuff. I'm going to call it S. Right, the other stuff in there. Okay, we can calculate moles of benzene. We have this molecular formula. So we can get its molar mass. I'm not going to worry about that. And I don't know how many moles of stuff I have. I need its molar mass. So this is equal to moles. In fact, I'm going to flip this. I'm going to be daft. To make it easier on myself, I'm going to raise each side to the negative first power. So I get P star B over PB is equal to mole B plus moles of stuff over moles of B. Now we have a binomial over a monomial, so P star B over PB is equal to, we can divide each term, 1 plus mole of S over mole B, right? Easier to calculate. Right, and this also implies that mole B times PB star over PB minus 1 is equal to moles of S. And moles of S is equal to the mass of S divided by its molecular weight. So solving for molecular weight, and I'm going this way. Right, so the molecular weight of S is equal to its mass divided by moles of benzene times P star B over PB minus 1. Okay, now we can punch stuff in. Cool. Right, so the mass of the stuff that we added, let's see, we had 10 grams, right? So 10 divided by moles of benzene. We need a smaller weight, right? So 12 times 6 plus 6 is equal to 12 times 6 is 72 plus 6 is 78, right? So this is grams per mole. So we take the mass of benzene that we had, which is 78.11, which is grams. We divide it by grams per mole, 78, and we get approximately 1 mole. A little rough enough to 1 mole. 1. And then P star is 0.93. The new P is 0.9. Right, so we have 10 divided by. This is going to be very, very close to. Exit it out. There we go. 0.93 divided by 0.9 is going to be very, very close to 1. And then minus 1. So that is 0.03. Okay, so then 10 divided by 0.03 is 333. Right, so the molecular weight is 333. This is in units grams per mole. All right, important steps in this. Recognizing that this is Raoult's law. I have no idea how to spell Raoult's law. I think there's an H somewhere in there. I forget though. Right, recognize that it's Raoult's law. Recognize that you can get moles of S somewhere in this mole fraction. Right, and from there, the rest of it is arithmetic algebra. Of course, there's not one way to do this. You could have just worked with it the way we had it before. It may have been easier. I'm not sure, but my brain just told me to reciprocate. So, yeah. Let's box the answer and carry on. Oh, this is the last. Oh, this is the last one. Okay. Oh gosh, how do you pronounce that? Reserpine. R. I'm going to call it R. R is a natural product isolated from roots of the shrub. Blah, blah, blah. It is a tranquilizer and sedative. When a gram of R is dissociated in 25 grams of camphor, like camphophenique, interesting. The freezing point depression is 2.63 degrees Celsius. The freezing point constant for camphor is 40 degrees Celsius kilograms per mole. Calculate the molality of the solution and the molar mass of R. Okay. So right away we can say that delta TF is equal to I'm going to assume that it doesn't dissociate because we have no way to tell if it's an electrolyte or not. So I'm going to assume that the Van Hoff factor is 1. Right? So Kf times our molality, right? So we can very easily solve for molality because we have delta T is given. Right? So our molality is equal to delta T F over Kf, right? So we have 2.63 degrees Celsius over 40. So let's run that really quick. So 2.63 divided by 40. So 0.066 moles per kilogram. Right? And we can actually use this. We're going to use this to solve for its molar mass. Right? So its molality is equals to mole of R per kilogram of, not water this time, it's camphor. Right? Right, so I'm going to move the kilograms of camphor to the other side. So we have kilograms camphor times M, and M is the N that we saw for up there. Moles of R is grams of R divided by the molar mass, our molecular weight of R, which is what we're looking for. We have the mass when 1 gram of that is added. So let's do some solving. Right, so the molecular weight of R is equal to grams of R divided by our molality times the mass, our kilograms of camphor. Plugging stuff in. Mass of R is 1, our molality is 0.066, and our kilograms of camphor is 0.025. Whoop, I just hit the mic. I am sorry if you're wearing headphones. Probably just scared you. Okay, so 1 divided by 0.066 equals, divided by 0.025 equals 606. Right, so the molecular weight of R is 606 grams per mole. And that is our answer for that. That is our answer for the molality. Okay, so I'm going to end this video here. It's been about an hour and a half. So I hope this helped. I'm not going to be able to do this all the time. It takes quite a bit. But if I see that I need to do that, then I may or may not, depending on if y'all like this or not, right? I can see how many of y'all viewed the video. So if a considerable number of y'all viewed it and comment on it, and stuff like that, then yeah, we'll go from there, right? Next Tuesday we will start kinetics. I'll see you then.